Welcome to the webinar on OSeMBE. My name is Hauke Henke and I'm working at the Division of Energy Systems Analysis at KTH, Stockholm, Sweden, and I'm the developer of OSeMBE, the open source energy model base for the European Union. In this webinar, I'm briefly introducing the open source energy modeling system, OSMOSYS, before then introducing the open source energy model base for the European Union, OSeMBE, going through its structure, the first indicative results, its strengths and weaknesses, and the way how to engage with OSeMBE, and concluding we will have a discussion on how the model can be used and how it can be further developed. Starting with OSMOSYS. Before explaining explicitly what OSMOSYS is, I would like to give an overview where in the energy systems planning context we can place OSMOSYS. In this figure, we have on the top the assessed years of planning tools and on the right-hand side the purpose divided by strategy and design. On the left-hand side, we can then see on what time frame is analyzed within the tools. So at the top left of the area of the graph, we have the stability analysis. So the very operative planning of a power system. And we go over load flow analysis down to power market analysis and down to long-term energy systems analysis on the bottom right. So the long-term energy systems analysis looks on the very long-term future, so up or between 50 and 100 years ahead, and has a strategic purpose. And in this area, we can actually place OSMOSYS. So we are looking on the capacity expansion and the shifts on the long-term plan and not on the operational planning. OSMOSYS, the open source energy modeling system, can be or is documented on the webpage osmosys.org and as well as in the paper OSMOSYS, the open source energy modeling system, an introduction to its ethos, structure and development and in energy policy by Mark Howells from 2011. The system is a model generator converting the energy system structure represented by equations into a matrix to be solved by a specific solver. But what does this exactly mean? Energy system structure is represented by equations. It means that the physical relations between parts of the energy system are represented by the mathematical functions. For example, our supply in this model has to be larger or equal to our demand. And the production of a technology has to be smaller or can maximum reach the absolutely maximum production possible of a technology in a year. And for example, the emissions have to stay below a certain limit, which has to do with or can be defined by the user. By these limits and boundary conditions, the user can define or characterize the energy system he is modeling. And this system is then linear optimized, which means to achieve the best outcome, so for example, the lowest cost or the lowest emission, but usually in OSMOSYS we're looking on the lowest cost. These mathematical relations are used to calculate this and to optimize the system in terms of achieving the optimal solution. Furthermore, OSMOSYS is, or very importantly, OSMOSYS is an open source and freely available tool. This has particular importance for decision makers and policymakers due to the fact that when numbers from models are used, it is important that they're traceable, or it is possible to trace back where they originate from. With the open source tool, firstly, the equations are accessible where or how the model is functioning, what assumptions are made, and secondly, in OSMOSYS, commonly the data is open as well, so the input data is also having an impact, of course, on the model outcomes. And by granting this openness and transparency, it can be analyzed and traced back how a certain result or indication was achieved. And based on that, the better judgment can be made than just looking on one single number. OSMOSYS is a deterministic modeling tool. Deterministic means that we give a certain input, for example, for demand, and it is not determined by the model. So the forecast or the assumptions on how the demand of, for example, electricity is developing has to be done beforehand, and it's not calculated by the model. The tool assumes perfect foresight, which means that we know the tool knows in advance all the demands, the fuel prices, and the cost of technologies, and how they will evolve through the modeling period. Overall, OSMOSYS can be compared to well-established modeling tools like Message or Times, which are used by international organizations like the International Atomic Energy Agency or, for example, the United Nations. Summarizing what OSMOSYS does, it is minimizing the overall discounted system cost of the system models. And this is on a domain of decades. And this minimization is constrained by the boundary conditions the user applies. So, for example, the characteristics of the technologies, emission taxation, or other constraints like the availability of resources. With this background knowledge on what OSMOSYS is, I would like to introduce now the open source energy model base for the European Union, which is an OSMOSYS model. OSeMBE is developed under the project REEEM, which is funded by Horizon 20 by the European Commission. And the task which was giving the order to develop OSeMBE is the development of an open source engagement model, a multi-regional engagement model aligned with input data and resolve more detailed tools, combining the key dynamics of the other tools used in the project. Translating this to a more common language, OSeMBE has to fulfill the purpose in the modeling project of being a communicative tool between sophisticated energy planning tools that are used in the REEEM project and policymakers and other stakeholders, as well as the and society, to communicate what dynamics and insights the project has gained, and therefore it's a tool that is a connection between the very in-depth energy modeling and the policy-making side. Talking about OSeMBE, I will follow these steps. I will first present the structure of OSeMBE before then giving an insight into the results and to indicate on where the results already have decent shape and where there are maybe still some shortcomings of the model. Let's start with the structure of OSeMBE. Firstly, how do we achieve engagement? In REEEM, we interpreted engagement to be enabled by accessibility and comprehensibility. The first is achieved by not having any license fees for the tool, by having open code and open data so that all the work done and the entire model can be taken and looked and be replicated. And secondly, the comprehensibility is created by making the tool as sophisticated as necessary to replicate the key dynamics by the more sophisticated tools, but keep it as simple in its structure that a non-expert understands what the model is doing or how the connections in the model are set up. So trying to follow this, we had to do the following decisions. We had to decide on a modeling system. Here we, as already indicated, decided on OSMOSYS. And for the model region, we decided that we stay on a country level. So every single country in the European Union, so all 28 plus Switzerland and Norway, are modeled. And fuels and technologies are aggregated to generic sets of fuels and technologies that are then, building the electricity system. As indicated, the model is covering the entire European Union and Switzerland and Norway, as shown here on the map. So all EU states and Switzerland as well as Norway. These countries are basically, or can be seen as single units in the model, or as regions, and those are connected by the possibility of exchanging electricity. For that, we are considering all existing transporter transmission capacities indicated here in red solid lines, as well as transporter transmission capacities that are currently under construction, indicated here by dotted red lines. The generic set of fuels and technologies is shown here. So first we have a set of fuels reaching from liquid biofuels over biomass, coal, a set of different types of electricity, geothermal, heavy fuel oils or oil products, hydro, natural gas, nuclear, which is based on uranium, ocean energy, solar energy, uranium, waste, and wind, which then can be used by a set of the technologies listed below. So not every technology can use every fuel, clearly. However, many fuels can be used by more than one technology. So we have, for example, offshore wind and onshore wind, as well as combined cycle power plants or gas cycle power plants. So overall, this sums up to 50 technology fuel combinations per country. You might have noticed here that pumped storage is indicated. However, storage is not considered in its whole, with its full characteristics. We're just using or considering pumped hydro storage power plants with their ability to produce power, but they are not able to store power, since this would have increased the complexity of the model significantly, and this would have meant that we would have needed a lot more computational power, which we wanted to avoid to keep the model, an engagement model. When looking into the model, you might see, or you will see, the technology naming or technology codes, basically, which are built according to the convention shown here. So we have first 2 letters indicating the country where the technology is used, and then 2 letters for the commodity, and then we have a technology that is using the commodity. So, for example, we have country Austria, and then the commodity coal, which is then used by a steam turbine. And then we have the energy level. This will get a bit clearer on the next slide. So we can talk about primary and secondary energy level. And we have the age, since for some technologies we have, let's say, old versions and new versions. So where the existing capacity is consisting out of the old version, but newly installed capacities will be the new version. And then we have the size for power plants where, the characteristics vary depending on the size. The same logic applies for commodity naming. So we have first the country and then the commodity, so that we end up with a name like, for example, ATCO for Austria coal. Here we have the reference energy system of Germany as an example, since a reference energy system of the entire model would be not readable. We see on the top level, we see the resources that are available in Germany, so coal, natural gas, crude oil, etc., which are then imported or extracted, depending if they're available domestically in Germany. And then they're entering the primary energy level, so the second level here in this graphic, from where they are then used in large centralized power plants, or they can also be passing this level. The transmission or the transport of those commodities is not modeled, and they enter the secondary level where they are used by distributed power plants, so smaller power plants. The electricity that is produced by large centralized power plants is taken by transmission and distribution system. This is the first box in the third row of boxes, and it's giving out the final electricity, and distributed generation technologies are as well producing final electricity. Furthermore, on the very right of this graphic, we can see electricity imports and exports for every connected country in the model. The country has one technology, so for example, Austria, Germany, electricity transmission, and this technology can either transfer electricity from Germany to Austria or from Austria to Germany. The key decision or design aspect for long-term energy planning models is the definition of time. Firstly, in OSMOSYS, we are looking on the time period 2015 to 2050, so 46 years. But furthermore, each year needs to be, for each year, time steps need to be defined. And for this, we use the approach shown here. So first, the year was split into seasons. Afterwards, the seasons were analyzed, if there should be, or how many typical days there should be per season, and those days were then split into time slices per day. And let's start with the definition of the seasons. Here we see a graph where we have in blue the capacity factors of wind, and in green we have the load, the overall electricity load in the European electricity system, or in the electricity system of the model countries, and which was used, or combined, these two graphs were used to identify seasons, which are then, or which are shown here by the red line. So each horizontal section of this red line is representing one season. So we have a very long summer season in the middle of the graph, and the first season lasts from day 1 till about day 61, which can be read on the x-axis. With these 5 seasons, we then went into, we then analyzed those 5 seasons in graphs like this one shown here. So the solid lines here are the average load profile of each weekday in the contemplated season. And we can clearly see that Saturday and Sunday have a significantly lower load level than the other days. However, since we had to consider that we want to keep our model light model, so not too complex, so that the computational time stays low, we decided that since the profile itself, even though lower, is quite similar to the rest of the week, we just have one typical day per season, which is indicated then by the red dotted line. Analyzing those typical days for each season, we used graphs like this one here. Here we are looking on season 1 and the day type of season 1. In red we have the load, so the average load for such for days in season 1, and in yellow we have the average solar capacity factor. And here the question was, or task was, to split or find times of the day with equal or similar load, and the solar capacity factor was considered to avoid that the time slices are cut in a way that there, due to averages, is, for example, availability of solar power during the night. So here we can see that in the red area, so in the graph, so the actual load, it starts increasing significantly at hour 7 and stops increasing at hour 9. So for 2 hours we have a ramping up of the load. And if we would just have considered the load, we might have put the end of the first time slice at hour 7 or 8. However, we see that the solar capacity factor starts increasing slightly earlier. Therefore, the first time slice ends at hour 6, so that the capacity factor is quite low, or is going close to 0 during the night time. And by the green bars, we see that we decided to have 3 time slices per day. So hour 1 to 6 is the first, the hours 7 to 21 are here the second, and the last 3 hours of the day, 22 to 24, is the third time slice. After implementing all the data and deciding on the time definition and having the model running, and already before that, validation and calibration process took place. So while building up the model, there was or an alignment with the input data of the time-span EU model from the University of Stuttgart was performed so that the technology input data is now in line and is comparable due to that. Resource estimates for used in OSeMBE are according or following the EU reference energy scenario for 2050, and afterwards, when the model was or is running, we did a calibration round comparing the results for the first 3 years, so 2015 to 2018, so where we have already statistical data with the actual numbers by the IEA. This indicated that the model is actually not using as much gas as is used in reality. So for the first couple of years where we, where the pattern was basically not changing much, but where we saw that too little gas is used, we implemented a minimum amount of gas that has to be used, which made the results look more according to the reality. Additionally, we had to put a constraint on how much capacity can be built per year of a technology. Most prominent here is or most importantly here is the limit that had to be put on the capacity addition of nuclear power. We assumed that it's realistic that not more than 3 gigawatts of nuclear power can be added per year in country. Knowing this, let's have a look into the results. The results provide already certain insights, but there are already also still some shortcomings. Here we see the overall power generation mix of the entire modeled region. We assume that the ETS path started or lined out already till 2030 is continued after that. So the emissions are continuously reduced. And we assume that the 10-year network development plan is not implemented. So after the introduction or after the first years where we have a not strongly changing generation mix, we see a reduction of the fossil fuels. So in dark blue and in black, natural gas and coal are reducing, whereas hydropower is staying constant, and biomass is strongly coming in, and nuclear is increasing slightly, nuclear in purple, but mainly wind power in lila is increasing. In pink, or not in pink, in rosa, we have the demand line indicated. The generation mix is it's producing more than the demand, since we're considering the losses due to the transmission and distribution. However, this is a very generic view of the results. Let's look a bit more in depth. Here we have 6 different countries. On the top, we have from left to right the United Kingdom, Germany, and Poland. And on the bottom, we have from left to right Spain, France, and Italy. And it is interesting to see that in the countries where there has been decided that nuclear is going to be banned, so namely in Germany and Italy, that both countries are, at least in the second half of the modeling period, strongly depending on imports, which can be seen by the gap between the rosa line and the generation mix. And in the other countries, nuclear is at least playing some role, and in the United Kingdom, France, and Poland, it's actually strongly increasing its capacities. However, it is also visible by Spain that if there is sufficient or good quality of renewable power plants that nuclear is not the first choice. So in Spain, we see that the large yellow area and the lila area are indicating that a lot of solar and wind power is selected by the model to be used. Let's have a look on the Transborder transmission in the model. In this graphic, we have all the modeled countries and their flows of electricity between each other. Starting at the top, we have Austria, and then counterclockwise, the countries are ordered in alphabetically order until we end up with the UK right next to Austria. The graphic has to be read in a way that if there is a gap between the bar of the country and the connections, and the connections going to the other countries, then it is an import to the country. So here, these ones are imports to Germany, and we see that Germany has just very small exports. We're looking actually on the year 2040. And what else can we see? We can see that Norway becomes a significantly and well-connected exporting country. So also under renewables, it stays like this due to its very good resources of hydropower, but also wind. But let's have a look on a bit more in depth. So we have already created 4 scenarios. So the base case that we contemplated already, where, as I said before, we assume that the emission reduction efforts continue on the path set by the ETS, and we kept the border transmission capacities at the level they are now, or rather just considered the capacities that are currently under construction as to be added. Furthermore, we created a scenario where the emissions are reduced fast. So we assume a decarbonized electricity sector 10 years earlier than in the other scenarios. And a third scenario where the emissions are following the path by the ETS, but the 10-year network development plan is completely implemented as recommended. And finally, we have a scenario where both of these modifications are happening. So we have fast emission reduction and increased Transborder transmission capacities. This leads to the generation mix as shown on this slide. So on the top left, we have the base case scenario, which we had already looked at. And then on the top right, we have the green scenario, which is the scenario where we have fast emission reduction, but no change in Transborder transmission capacity. On the bottom left, we have the integrated scenario, where we have increased Transborder transmission capacities. And on the bottom right, we have fast emission reduction and increased Transborder transmission. Not surprisingly, due to the emission limit, we can see that in the green scenario and in the gray scenario, all fossil fuel technologies are phased out by 2037 approximately, and also before the production is slightly smaller. But overall, the general trends are not so different, but we can see that biomass is clearly hitting the limitations that are implemented according to the resource availability, since from 37 onwards, we have a very clear line that seems to be not increasable. But let's look a bit more deeper. So here we have the generation mixes of all the 4 scenarios for 2040. Interestingly, in my opinion, is that in the integrated case, the bar of coal, so the black stripe at the bottom area, so above biomass in green, seems to be slightly stronger than in the base case, whereas in the other two scenarios, it has disappeared since there are no emissions allowed anymore. And this might be due to the fact that there are countries where domestic coal resources are available, and due to the higher transporter transmission capacities, these countries are then exporting coal-based electricity. If we compare the scenarios or the transporter transmission under the scenarios, here we have first the base case again, and then the green case. Interesting is, which might not be readable, is that the overall transmitted electricity is decreasing from the base case to the green case. So faster electricity, we're looking again on the year 2040, but a faster emission reduction with the same amount of transporter transmission seems to lead to slightly reduced exchange of electricity. And when looking at the integrated scenario here, of course, we have a way larger trade volume since the capacities are there, and we can see, however, the general pattern doesn't change significantly. So, for example, Germany in the center of Europe stays in all three scenarios. Importing country in the integrated scenario, actually, there are no exports at all. And when we combine integrated and green, we get this scenario, and here the overall trade volume actually has increased significantly as well to the integrated scenario. So in this case, the increased speed of emission reduction leads to a higher usage of the transporter transmission capacities. So having this model, how do we enable the engagement? Another element of the REEEM project is the so-called REEEM game. It's a game where single player or multiplayers have to achieve have to vary decision parameters to achieve a higher score on the performance of their region or of the entire continent. And this game has in the background the results of a lot of scenarios run with the OSeMBE model, and this game is basically ready. And the runs with the OSeMBE model are still currently going on. That's why the game is not yet available. And furthermore, except from the REEEM game, OSeMBE is already being used on master thesis or on master studies level, so in courses, but as well for master theses, the model has been used and is used, and the model is used in workshops and in webinars like this. However, it has to be added that there's still some, or unfortunately, there are also some obstacles for engagement. The model turned out, even though we kept the structure quite simple and had this always in mind when making decisions on how to design the model, needs quite strong computers. So currently the model is running on computers that have 250 gigabytes of RAM, and the process of processing the results and also the input results has to be improved or has to be changed, since the model was firstly developed using the open source graphical user interface, which is built for OSMOSYS, called More Money. However, the large amounts of data slowed this, or were not handleable by the user interface. Due to that, unfortunately, the work is now done on text files. With this, I would like to, before concluding this webinar, I would like to indicate that the model and the data used and documentation and the license file are available on osmosys.org, where it can be downloaded by everyone and checked. Now I would like to conclude this webinar with a session with questions and discussion. During the last minutes, I received a couple of questions by the chat, which I would like to read out now and then to answer. Question number 1 is, what is your view on how the stakeholders could contribute to the validation and enhancement of the model from now on? I think, or in my opinion, the best way of engaging with or improving the model is when using the pathway diagnostics tools or the REEEM game with them, and then by having discussion rounds or workshops on how reasonable those results look like, or why those results look like that, and either it's then identifying that it's explaining something, or it's possible to identify not ideal assumptions of the model, and by this divergence of expectations and outcome, the model can be improved. Is the data available? Yes, as just indicated before, the data of the model, or the data used of the model, so the data file, is on osmosys.org and can be downloaded. It's complemented with a license file which contains all the sources used. And furthermore, there's a the written documentation, which is also again explaining how are the technology names and how is the model structured. The next question is, what are the next steps in the development process? I mentioned a couple of the steps. The next step is to finish the scenario runs that are needed to get the REEEM game running, and then to implement those into the REEEM game. And finally, to improve, and afterwards, the next step would be to improve the infrastructure around the model so that it can be better used also in classes for students to, for example, work on country models and improve those country models, and then add those again to the large model. And perhaps we would like to also add some more sectors, since we're just covering the electricity sector at the moment. And so the next question is actually, are there any plans to add additional sectors? Yes, there are. This is intended, but this will not happen anymore in the REEEM project, since REEEM is going to end next year. And however, as I said, it is currently it's definitely exceeding most normal laptops, the model. So one issue that is related to the extension of the model is how can we make the model lighter or easier to calculate so that it still can stay an engagement model which is usable by normal notebooks. And what are the exact numbers on, or what are the requirements for the hardware on running OSeMBE? Currently, when I run the model, it takes 6 to 7 hours on a computer with, as I mentioned, 256 gigabytes of RAM. And I'm using the solver Cplex by IBM, which has a free license for academics. And then for the visualization, I'm using Excel. Good. With this, I would like to conclude if there are no further questions. And I'm happy to receive further questions either, or ideally via the OSMOSYS forum. Goodbye. Thanks for the attendance.